Welcome back, everybody. This is chapter 13, uh, Evidence of Evolution. And again, as we begin this chapter, this is the second part, if you will, in this unit, chapters 12, 13, and 14. And again, this is going to be our last set of notes for the semester. So getting close to the end here. So again, chapter 12, we talked about evolution, and again, how evolution works. Evolution's, as we said, one of the tenets of life. Things change over time; they adapt, and of course, if they don't, then they become extinct. So we'll look at some of these events and this evidence of evolution as we go through chapter 13 here. And we start out with a slide here that shows the fossilized bird. Again, fossils obviously a good indication that there were things here that no longer are. So again, this number here changes, that life on Earth rose around 3.8 billion years ago. So you will see from time to time somebody will find something it's earlier than what they thought it was, or later what they thought it was. When you're talking about geologic time, this is a vast time scale. So obviously, pinpointing exact dates and times is not going to happen. So you get rough estimates, and again, with a geologic time scale, you kind of go back to the beginning, when Earth was, the origin of Earth about 4.6 billion years ago, and then life starting somewhere in here. So again, it's changed over time. There's been a lot of different eons, epochs, and eras, as you can see here. Some of these names may be familiar to you, but again, a lot of change, obviously, over time, and a lot of things that we have now that have come to us from, many years from the past. And when we look for evidence of previous life, obviously one of the great ways to do that is to look at fossils and molecular sequences to learn how species are related to one another, finding commonalities, some origins, and things like that. And again, if you're into that type of thing, paleontology is a study of fossil remains or other past life, and looking at clues of that. I know here, in our area, there are several places you can find fossils. Clarita has some trilobites. In our next slide, we'll see, and go ahead and pull that up. The ammonites, my wife's aunt has some ammonites over in Love County. So there's a lot of these, obviously, organisms that are no longer with us that are obviously indicative of things that used to be. And in fact, it says fossils help researchers piece together Earth's history. For example, these marine fossils from landlocked Oklahoma show that water once covered the central United States, and that's true. My wife's aunt has on her property these ammonites, but it also has a lot of other seashells, and in fact, you can actually see the Earth's crust has kind of moved and tilted. That old seabed has moved up and jetted away from the existing soil structure. So again, we're talking about a long period of time ago when we were underwater here and we had these sea creatures floating around us. So dating fossils, again, there's one way. We mentioned this in the previous chapter, relative dating, where basically you assume that the newer fossils would be higher, and then the older fossils would be lower into the soil. Now that's problematic because, again, erosion over time can make these fossils fall from up high to down low. So that's not a really accurate way to do it. And if you want to do it accurately, we have absolute dating, which uses chemistry to determine how long ago a fossil formed. Radiometric dating is a type of absolute dating that uses radioactive isotopes. Carbon-14 is probably the most famous one of those. Carbon-14 has a half-life of 5,730 years. And you can see that on the scale here. So basically half of it rains after 5,730 years. And again, throughout the life of an organism, you accumulate carbon-14 along with a stable carbon-12, which again are isotopes of carbon. And these living organisms have a constant amount of carbon-14 tissues up until the time they die. After you die, no more is put back in. So this constant rate of decay, 5,730 years, allows us to date a lot of fossils. So again, you would expect half of that amount in the carbon-14 into the bone structure to be present after 5,730 years. And then half of that, again, would be another 5,730 years. And you do the math of that, and that's a roughly 11,000 some odd years here. So again, you multiply by 2 here, there's 1 half-life, there's 2 half-lives, 3 half-lives, 4 half-lives. So you kind of understand how that works. So 4 half-lives would be 5730 times 4, and that would tell you the age of that fossil. Carbon-14 dating is very, very common for bones, especially that are again, assumed to be very old. For dating fossils, it's a good way to do that. Biogeography also helps us piece together, you know, the land masses and how kind of things were situated. It says Earth's geography has changed drastically over the last 200 million years. And again, these time frames are so vast, it's hard to, you know, wrap your mind around it a lot of times. It says these images represent only about 5% of Earth's history, in fact. So 200 million years, again, we can't hardly fathom that, much less billions of years. But you go back again, you know, to the giant continent of Pangaea. If you've ever heard of that word before, when the continents were connected. Continents are set on tectonic plates, and these tectonic plates, again, are what these continents move around on. And again, a theory, but we know that there are tectonic plates. We see evidence of tectonic plates. Earthquakes and volcanoes are evidence of that they're moving today, where we have these, you know, these great continental divides. They rub, they shift, causes friction, cause volcanoes, earthquakes again. And you see kind of how over time these continents broke up, moved away from each other. And this has actually probably happened many times in many different formats in Earth's history here. So again, our continents are continuing to move. Now, again, obviously they don't move very fast, but again, we see evidence that they were used to be connected, and we call that biogeography. So some fossils, again, are found in different areas. For instance, Triassic period reptiles are found in South America and Africa. And if you connect the pieces together, like, again, what it used to be, you can see that that has a vast swath there that kind of fits nicely with it. Same thing here for the Permian. Those fossils, again, you can kind of see where they're connected. So again, these land masses at one point in time used to be connected with each other. And again, you know, we can kind of draw lines and kind of sequester animals based upon where they're found. If they're more like Asia, you would find those west of this, what is called the Wallace Line. Now, Wallace should be a name that's familiar to you. Alfred Russel Wallace was the gentleman who, along with, you know, I just drew a blank there, of one of the most famous men of all time, Alfred Russel Wallace, and you know, his work with you know, finding, you know, natural selection, and Darwin, there's Darwin's name, coming out and saying, you know, if you actually draw a line here, you can find animals that are more like Australia or more like Asia on either side of this, and it's known as the Wallace Line, meaning that, again, depending on where these continents were at that time, a lot of those animals separated via this line. So we look at anatomical relationships between commonalities and common descent. We find that there are some structures that are homologous, that if they respect common ancestry, that they have the same bones. It says all these animals, for example, have similar bones in their forelimbs. We don't use our bones all in the same manner. Some used for swimming, some for flying, obviously humans to lift things. But again, all of us have that same bone, that same homologous structure that we use in the same way. Homologous structures don't have to look alike. They don't have to function exactly alike. They just show that we have the same things there that led to these changes, obviously over time, but we all have that same bone. Vestigial structures. means that it has lost its function, but is homologous to a function structure in another species. Vestigial hind limbs, for instance, in some snake species, as you see here, these femurs, and in whales with the pelvis, again, they don't need them. But there are remnants of, again, when the whale probably was on land and had a pelvis before it became totally aquatic, and when a snake had legs. Now, again, I think there's a lot of things that we can talk about, in terms of this part of the evolution that, again, depending on what your thoughts are, that justify a lot of things, and we talk about the earth being underwater, the flood event, which is, again, a part of a lot of different religions, not just Christianity with Noah's Ark, but other religions as well, that the earth was covered in water. We have, obviously scientific evidence of that we were underwater here, that the snake used to walk on land before he tricked Adam and Eve, obviously. So it is kind of interesting that the snake has femurs, which are, again, needed for legs, but obviously no longer has those legs. Anatomical structures are analogous if they are superficially similar but do not derive from a common ancestor. It says none of these cave animals have pigment or eyes. These similarities arose by what is called convergent evolution, which produces similar structures in organisms that don't share the same lineage. Lack of pigment arose independently in each of these cave animals. So it wasn't something that they all shared. It's just that if you live in a cave, it's beneficial not to use energy on eyes and pigment and put it somewhere else. So again, over a long period of time, these things occurred. Now, anatomical structures or similarities are often noticeable, especially in the embryonic stage. You see the chimpanzee and the human fetus here. The skulls are very similar, but obviously very different once the full adult structure is realized. And again, a lot of things look very similar at the embryonic stage here. So you look at the alligator, mouse, and the fish. Obviously, they're not exactly the same, but they have, again, a kind of a similar look. So how do they develop into different organisms? Well, it's homeotic genes. So homeotic genes actually control an organism's development. Small differences in gene expression might make the difference between a limbed and a limbless organism. For instance, homeotic genes help explain why there might be a few key mutations that produce a new species. For chickens, basically, their tail gets turned off and they develop wings, whereas a python snake, their hind limbs remain vestigial. They don't develop and they have the tail, and they don't have, again, the forelimbs are absent, so they don't have to worry about having wings, obviously. But again, what's interesting about this is there are genes that turn on and turn off, much like what we talked about, again, genetic expression before, pleiotropic events. One gene may turn something on, one may turn it off. Would it be possible for the genetic engineering that we turn that limb on? Yeah, that's a possibility, obviously, genetic modification. If we know what causes it to turn off, can we turn it on? And again, it's not the question of can we, probably, it's probably should we turn it on. I mean, snakes are scary enough as it is, much less one that's got a set of legs coming at you. So again, a lot of things there that we have figured out, and now it's a matter of, do we want to mutate these things in a lab setting? So a lot of questions arise from that. Now, molecules themselves reveal how much alike we are. So we talked about in a couple of chapters ago that we are very much like chimpanzees. In fact, 99% of our DNA are similar. Now, again, that 1%, if you remember, is about 3 million base pairs, that are still different, and that's a lot. But if you compare us to other things using these cytochrome Cs, these mitochondrial proteins, you see that we are more like chimpanzees than we are a rhesus monkey, for instance. More like a rhesus monkey than a rabbit, than a cow, and all the way down to wheat and yeast. Obviously, there's a lot of differences between us and these things down here. And we're a lot more similar to chimpanzees, obviously, in terms of our genetic makeup. So these molecular clocks are basically used to assign dates to evolutionary events. So if a gene is estimated to mutate every 25 million years, then two differences from an ancestor might arise in 50 million years. Therefore, the two species that derive from the same common ancestor 50 million years ago might have 4 differences in the nucleotide sequence of the gene. So again, might have had a common ancestor, a mutation occurs, they change, they split. Another mutation occurs, they continue to split, and they're on tracks here. And we have, the common ancestor, and we have modern species in here, and the difference in their genome. And again, look at the geologic time here, 25 million years. That's incomprehensible. For us mere mortals that try to work through these things, that concept of that vast time period and the mutations that occur there is really hard to fathom sometimes. But again, you can see where over millions of years, obviously, there would be some changes. So the last part here talks about evolving backwards. It says we've already seen evolution does not always lead to greater complexity. In fact, sometimes you lose features like legs from the snake and pigmentation and eyes for the salamander. Obviously, it works better for them because the snake doesn't have to worry about his legs getting hung up in a burrow. Okay, this guy here, again, the salamander, he's in an environment without light, so pigment provides no selective advantage for him. And because he saves energy in pigment production, he is more suited to his environment. So again, sometimes less is more. And if you don't need the legs, why have them? And again, wasn't that, again, I'm going to touch on this before we wrap up for this section here on this chapter. It's not that the snake knew that he didn't want legs. It's that evolution preferred, obviously, that it didn't have legs. It was easier for it to hide and burrow in than if it had legs. So that got bred out over a long period of time. And again, a time frame that we're just, having trouble, again, as humans understanding. But again, over a long period of time, it was an adaptive thing that worked for the snake. Okay, so that's the end of chapter 13. Chapter 14 is pretty short as well. And that'll wrap up our unit.